presentation. First, I will introduce GANs and their basic idea. Then, I will explain the architecture of GAN, including the generator, discriminator, and loss function. After that, I will discuss applications, challenges, and finally conclude the presentation. Introduction. Generative adversarial networks or GANs are used to generate new and realistic data by learning patterns from existing data. GANs were introduced in 2014 by Lan Goodfellow and his team. Since then, they have significantly changed how machines create content. A simple way to understand GAN is through an analogy. The generator acts like a counterfeiter trying to create fake data. The discriminator acts like a detective trying to identify whether the data is real or fake. Both models compete with each other, and through the competition, the generator learns to create a very realistic data. The ultimate goal is to generate synthetic data that is indistinguishable from real data. Now, the architecture of GAN. GAN consists of two neural networks that work together, the generator and the discriminator. The training process works in a loop. First, the generator takes random noise and create a fake image. Then the discriminator compares the fake image with real images from the dataset. The discriminator outputs a probability score between 0 to 1, indicating whether the data is real or fake. Based on the feedback, both networks improve themselves. Over time, the generator becomes better at creating realistic data, and the discriminator becomes better at detecting fakes. Generator. The generator takes random noise as input and converts it into fake data such as images. Its main objective is to fool the discriminator by generating data that looks real. The generator learns by minimizing its loss function, which measures how successful it is in confusing the discriminator. In simple terms, the generator tries to maximize the probability that the discriminator classifies its fake data as real. As training progresses, the quality of generated samples keeps improving. Discriminators. The discriminator acts as a binary classifier. Its job is to distinguish between real data from the dataset and fake data produced by the generator. For image-based tasks, the discriminator usually uses CNNs to extract features efficiently. The discriminator tries to correctly classify real data as real and fake data as fake. Its loss function measures how well it performs this classification task. So while the generator tries to fool the discriminator tries to become more accurate. GAN loss function. The GAN loss function is based on a minimax game between the generator and the discriminator. The generator tries to minimize the loss while the discriminator tries to maximize it. This creates an adversarial learning process where both models continuously improve. At equilibrium, the generator produces data that is so realistic that the discriminator cannot reliably tell the difference between real and fake data. Application of GANs. GANs have a wide range of real-world applications. They are used in image synthesis, such as generating realistic human faces and artworks. GANs help in medical imaging where data is limited. They are also used in style transfer, for example, converting photos into paintings. Other important applications include super resolution, that means the we improve the quality of the image, art and content creation, medical imaging, and face synthesis such as deep fakes and digital avatars, etc. challenges and limitations. Despite their power, GNs have several challenges. Trading GNs is often unstable and may suffer from problems like mode collapse, where the generator produces limited types of outputs. Evaluating GN's performance is difficult because there is no single perfect metric. There are also ethical concerns such as misuse of defects, misinformations. Additionally, GNs require high computational resources, including powerful GPUs and large dataset. Conclusion To conclude, GNs are powerful generative models and play a crucial role in modern deep learning. They are widely used across AI, healthcare, media, and creative industries. Also, GNs are challenging to train. Ongoing research continues to improve their stability and performances. Understanding GNs is very important for anyone working in advanced machine learning and artificial intelligence sector. These all are my reference for my presentation. Thank you for your time and attention. Thank you.